Hello everybody, welcome into another lesson. So today we are going to talk about concurrent lines and what those mean for triangles and proportional lengths. So, concurrent lines are simply put, they're two or more lines that intersect at one point. If you have two or more lines that intersect at one point, those are called concurrent lines. And I have our first theorem here that pertains to triangles. The theorem states the bisectors of the angles of a triangle intersect in a point that is equidistant from the three sides of the triangle. So here we have triangle ABC, and then if you look through here, you have ray BE that bisects angle B, ray CD that bisects angle C, and ray AF that bisects angle F. The point where they all meet is G. Well, from point G, it is equidistant to side AB, to side AC, and to side BC. So in other words, segment DG, the distance from where the bisectors meet to where they come to the other side to D, segment DG is congruent to segment EG, which is also congruent to segment FG. I know this triangle is probably not the best representation, but you'll get the point. So let's do a couple exercises here. This is a fairly simple, easy one to understand. Let's say that DG has a length of 2. We don't know the length of GE, and then we don't know the length of FG. So we'll call the length of DG a length of 2, the length of EG would be X, the length of FG would be Y. Well, according to this theorem that I have up here, the bisectors of the angles of a triangle intersect in a point that is equidistant from the three sides of the triangle. So that means this point G is equidistant from all three sides. So if DG is 2, that means EG, which is X, would also have to equal 2. So you'll get a value of X that equals 2, and then you'll have FG, which has a value of Y, Y would also equal 2. So that's what that theorem means. Let's do another one here. Let's say the next one has a length of 9.82. Say DG has a length of 9.82. This time FG will be X, EG will be Y. Well, according to this theorem, EG and FG would have equal lengths to DG. So X would also in turn equal 9.82. And then Y itself would also equal 9.82. So this is a pretty simple theorem to understand, that the angle bisectors all intersect in a point where that point is equidistant from the three sides of the triangle. And let's see, I have another theorem here. What's the next theorem say? This one says the perpendicular bisectors of a triangle all intersect in a point that is equidistant from the three vertices of the triangle. Let me draw an illustration for this one here. We'll name this one again triangle ABC. Alright, we need to find the perpendicular bisectors here. Pardon the nails on the chalkboard. Not the most bisecting, but whatever. Alright, so first off, in just a minute here, we're going to talk about what a perpendicular bisector actually is. But first, let's label some points here. D, E, F, and the point where they meet is G. Alright, well, probably not the best illustration again, but you'll get the idea. So, this theorem states that the perpendicular bisectors of a triangle all intersect in a point that is equidistant from the three vertices of the triangle. So the last theorem stated that the angle bisectors of a triangle all intersect in a point that is equidistant from the three sides of the triangle. This one is different. This is the perpendicular bisectors of a triangle all intersect in a point that is equidistant from the three vertices of the triangle. Of course, a little review, what is a perpendicular bisector? I think everyone knows what an angle bisector is by now, but what is a perpendicular bisector? It goes from one vertice of a triangle to the midpoint of the opposite side of the triangle, and it is perpendicular to the opposite side at its midpoint. Thus, it's a perpendicular bisector. So, you have triangle ABC, then you have point D, where ray CD comes to side AB to become the perpendicular bisector of side AB. Then, of course, on side AC, you have ray BE that meets side AC at the midpoint of AC to become the perpendicular bisector of AC. And then here you have point F, where ray AF meets side BC to become the perpendicular bisector of BC at its midpoint at point F. And the points where all the perpendicular bisectors meet is point G. So this time they're equidistant from the three vertices. So in this case, we can say that segment BG would be congruent to segment CG, which would also be congruent to segment AG, though I know it doesn't look the best, it truly is. So from point G reaching to A, that's going to be congruent to point G reaching to B and to point G reaching to C, the three vertices of the triangle. And let's do a couple of exercises that demonstrate this theorem. Okay, so what if I assign BG to have a length of 7? BG has a length of 7, okay? CG has a length of X, AG has a length of Y. We're going to solve for X and Y. Well, according to this theorem then, BG, CG, and AG are all equal, so therefore X would also have to equal 7, and then Y would also have to equal 7. You would have 3 equal lengths there from where the perpendicular bisectors meet. And then This time, let's do it with 23. So this time BG has a length of 23, CG has a length of x, AG has a length of y. Well, according to this theorem we just learned, x and y would also be equal to the 23. So x equals 23, and then y also equals 23. So that's another pretty simple theorem to understand. And then I have two more theorems. One's actually really short. This one's a really short one. The lines that contain the altitudes of a triangle intersect at a point. That's all this theorem states. And let me draw a triangle to illustrate that here again. Well, triangle A, B, C. Of course, we're going to talk about altitudes here in just a minute, but all right, just a minute here. Let's see, I will label each of these points, and point G is where they all meet. Okay, so this theorem states that the lines that contain the altitudes of a triangle intersect at a point. Well, that almost seems like no duh. Really? You figure? So again, we have triangle ABC. Here we have the three altitudes. Well, first off, what are the altitudes of a triangle? The altitudes are drawn from a vertice to the opposite side, and they're perpendicular to the opposite side. They're always perpendicular to be the altitude. Now, the problem is you're not going to know the lengths of any of these unless you know the angles and can do trigonometry, which that's coming up here actually shortly. Not in today's lesson, but in a few lessons from now, we're going to do a little bit of trigonometry. But for now, there's really no way to know the lengths of these. They're not quite equal. Unless you have an equiangular equilateral triangle, then they would all be equal. At which point your altitude also is your median, is also your perpendicular bisector. And an angle bisector at that. It's all four of them in an equilateral triangle. So then you would have equal lengths. But in this case, we don't know the length. So that's the best we can do for that one. Okay, the one last theorem, which is really the meat of today's lesson. This is a big one. The medians of a triangle intersect in a point. Now this is where it gets interesting. that is 2/3 of the distance from each vertex to the opposite side, to the midpoint of the opposite side, I should say. Okay, let me draw a triangle here to illustrate this again. It always helps to have an illustration of this. We'll name this triangle ABC. This is definitely the biggest theorem of the day. All right. Well, that'll be point D here. Okay. Right here is going to be point E. Then I got one more to draw for good measure, right? We will call this point point F, and the point where they all intersect will be point G. Okay. First, let's talk about what are the medians of a triangle. The median comes from a vertex of a triangle to the midpoint of the opposite side. That's all a median is. It doesn't necessarily mean it's perpendicular to it or that it's an angle bisector. That would all depend on the angles you have in the triangle, but the median just simply runs from a vertex to the midpoint of the opposite side. This theorem states that the medians of a triangle intersect in a point that is 2/3 of the distance from each vertex to the midpoint of the opposite side. So what does that mean? Well, if you look at this here, AE, right? Ray AE goes from vertex A to side BC. This is the median of side BC, so E is the midpoint, right? Well, what does that mean? Well, AG and EG make up ray AE, do they not? Or segment AE, I should say. What that's saying here, if we look at that exclusively, is that AG is 2/3 of the distance from A, which would have to mean that it's only 1/3 of that. That would have to mean that GE is 1/3 of the distance from the opposite side. So AG is going to be 2/3 of AE, and then EG is going to be 1/3 of AE. That's what that really means. All right, so you have AE, which is the median from vertex A to side BC. that means that AG is equal to 2/3 of AE, and then GE is equal to 1/3 of AE. And then likewise here with, okay, let's look at FC or CF. Well, that means that CG, since G is 2/3 of the way from vertice C, that means that CG would have to actually equal 2/3. CG is equal to 2/3 of CF, which would have to mean then that FG would be equal to 1/3 of the distance of CF. That's exactly what that would mean. FG would be 1/3 of CF. And then you guessed it, let's go over the final median here. Let's do the final one. So if we look at the whole BD, that's the median from vertex CB to side AC, that means that BG is going to be 2/3 of the distance of BD. And then you're going to have then that DG would be 1/3 of the distance of BD. And that makes sense because if you add 2/3 of BD plus 1/3 of BD, well, you get BD, and then BG plus DG equals BD. So either way, that really makes a lot of sense. Now we're going to do some exercises to put this into practice. There will be several exercises of this, even a little bit of algebra. Okay, so let's see here. Let me draw what they have. I'd like to really make this a big triangle for you guys. Here's A. That's point A. Here's B. Now, let's see here. And then where all three of these medians meet is point P. Okay, so we have a triangle here. They don't give you all the vertices. That's okay. Trust me, you don't need them. This is X. This is Y. This is 3. This is 5. Okay. Well, we need to find, to start with, we're going to find X and Y, are we not? So remember this theorem here. We have the medians of a triangle meet at a point that is 2/3 the distance from the vertice to the midpoint of the opposite side. Well, let's solve for X, okay? From P to this vertice here, from P to this vertice is X, and then from P to the midpoint of this side is 3. So 1/3 of the side, I should say 1/3 of the median equals 3, right? Well, that means from P to this vertice, that's 2/3 of the distance. To do 2/3 of the distance, you just multiply both sides by 2. So x would equal 2 times a third of the median, which would end up equaling 2 times 3, which means that x would have to have a length of 6. So from P to this vertice then, that's 2/3 of the distance, which would just be twice the distance from P to this midpoint. So 2 times 3 essentially gives you 6. Now how about y? In fact, let's fill this in here. Since we solved for x, let's go ahead and fill that in now for being 6. Alright, so let's solve for y. Well, we know the distance from P to this vertice is 5, right? Which means that's 2/3 of the distance of the line. So 2/3 of the median is equal to 5, right? Well, in order to solve for y, that's going to be half of 2/3 of the median, which would have to mean that that's going to be half of 5, which half of 5, as you know, is 2.5. So y would generate a value of 2.5. And this is going to stay here for all the exercises. So y is going to generate a value of 2.5. Okay, so now we got the lengths between those two medians. Now for the next 3 exercises, we're going to figure out the lengths of AP and PB and AB. So let's go ahead and do just that. Yes, so this is where proportional lengths really come in handy. Alright, so what do we got here for this one? If AB equals 6, then AP equals what? And BP equals what? Okay, so the length of median AB is 6, right? Well, according to the theorem we just learned, the distance from A to P is 2/3 of the distance of the whole median. So AP is simply equal to 2/3 of the distance of AB, which would end up giving you then that you would have 2/3 times 6, which would be equal to 2 times 2, which would have to mean that AP is equal to 4. So the length of AP is 4, and then we could say that the length of BP is equal to 1/3 of AB, which would have to mean that it's 1/3 of 6, which means that BP has a length of 2. So AP in this case has a length of 4, BP has a length of 2. Alright, let's see here. I think it's similar exercises, but a little bit different. Alright, so this time AB has a length of 7. So we know that AP, again, AP has a length of 2/3 of AB, which would be equal to 2/3 of 7, which would equal what? 14/3, which has to mean that AP ultimately is going to be equal to 4 2/3, which is approximately equal to 4.67. So AP has approximately a length of 4.67 if it's 4 2/3. Now, of course, we have to figure out the length of BP, which would be a third of the length of AB. That's equal to 1/3 of AB, which would mean it's equal to 1/3 of 7, which would give you 7/3. That would be 2 1/3. So BP is approximately equal to 2.33. 2 1/3, which, if you add the two lengths together, you would end up getting 7 for your whole AB. Now this is a good one. Let's see. AB this time has a length of 1.9. So AB just has a length of 1.9. So again, AP is equal to 2/3 of the length of AB, which would be equal to 2/3 times 1.9, which, what would that give AP equal to? Let's find 2/3 times 1.9. Since there's a decimal, it gets messy. That's approximately equal to 1.27. So AP is approximately equal to 1.27. Now we need to find BP. BP, of course, would equal a third of AB, which would then mean that it's equal to 1/3 of 1.9, which would give you an approximation here. So let's see, 1 divided by 3 times 1.9, that's about 0.63. So BP has a length of approximately 0.63. And if you added these together, I guarantee you, you would get 1.9 for the total length of AB. So that's that theorem at work so far. Now there are 3 exercises I want to do to demonstrate this theorem with some algebra. We're going to do 3 algebraic exercises. And these are some good ones because we actually have some quadratics. So it's a much needed review. Alright, let's see. CAB. Okay, there's triangle CAB. We're going to deal with the medians again here. The medians, and then alright, let's identify our points here. Of course, that's going to help us. Let's see, V, W, U, and then the point where they meet is at point P. Okay. So, for the next three exercises, we're going to be staring at this triangle here, where each of the three medians meet at the special point that is 2/3 of the distance from the vertice and 1/3 of the distance from the midpoint of the opposite side. Okay? So let's start with our first one here. If AP equals x squared, and PU equals 2x, then x equals, good news is we only got to solve for x. So, we're given here AP has a length of x squared, PU has a length of 2x, then we got to solve for x. Well, we're only looking at median AU. That's all we're looking at for the time being. What do we remember here? That based on the theorem, AP is equal to what? That's equal to 1/3 of AU, or it's equal rather to 2/3 of AU. I'm going to illustrate the point here. AP is equal to 2/3 of AU, which means that PU equals 1/3 of AU. Do we notice anything here? If AP is 2/3 of AU, and then PU is 1/3 of AU, what does that mean? That means that AP, you can also argue that AP is then equal to 2 times PU, could you not? Because if AP is equal to 2/3 of AU, PU is 1/3 of AU, that means AP is twice PU. Now it's easy. All we have to do is substitute the values in here. AP is equal to x squared, right? That means x squared equals twice the value of PU, which would be 2 times 2x here, which would then give you that x squared equals 4x, which would then give you x squared minus 4x equal to 0, which would factor into x times x minus 4 equal to 0. Well, take your two solutions, you would have x equals 0, and then x minus 4 equals 0 will give you x equals 4. Well, right away we can discard that 0 because you're not going to have a 0 length. That just isn't going to happen. So your only solution here in this case is that x would equal 4. So basically, if you can understand in this case that the distance from the vertice to where the medians meet is twice the distance from where the medians meet to the midpoint of the opposite side. If you can understand that, this will be easy. And I got 2 more exercises with this. It's going to change up a little bit though. Let's see what we're up against this time. Alright, what do we got here? I might write over here this time just for simplicity's sake. So, I'm going to erase these so we don't get confused. Because we're done with this median now, we need to find the other two. But first, we're going to find another one. If BP equals y squared plus 1, and PV equals y plus 2, then y equals what? Alright, this is going to be a very interesting one here. So, Let's take a look at this. If BP, which BP's right here, has a length of y squared plus 1. So let me put that right here. BP has a length of y squared plus 1. And then PV has a length of y plus 2. Right? Okay. What do we understand again? That BP is equal to what? 2/3 of BV. Which would have to mean that PV is equal to 1/3 of BV. Well, if BP's 2/3 of BV and PV's 1/3 of BV, that simply means then that BP is equal to twice PV. So BP equals twice PV. So now it's just a matter of substituting the values in. BP was y squared plus 1, so you'll have y squared plus 1 is equal to twice the value of PV, which was y plus 2. Which will do the distributive property. You'll get y squared plus 1 equals 2y plus 4. Now, of course, we have a quadratic equation we got to solve. If we simplify this first, make the right side equal to 0, this will simplify into y squared minus 2y minus 3 would be equal to 0. Now, of course, we can go ahead and factor this. You're ultimately going to have then y, let's do the y's here. Definitely a 1, definitely a 3, but in what order? So you have y squared, minus 3y plus y would give you that negative 2y, then minus 3. Of course, now we take each solution, set it equal to 0. Y plus 1 equal to 0 would give you that y equals negative 1. And y equals 3. Now, let's input both solutions into these values. If you put negative 1 into BP, well, negative 1 to the second power is what? That's just positive 1. Then add another 1, that's 2. And then if you put negative 1 into PV, you would end up getting negative 1 plus 2, which would be 1. So actually, negative 1 in this case is a viable solution because you're not going to get a negative length. The overall length will not be negative, so y can be negative 1. Now, let's input y equals 3 into BP. Of course, 3 to the second power is 9. Add 1, that's 10. Then if you put 3 into PV, put that in for y, 3 plus 2 is 5. So actually, you would have two values for y. They both check out, negative 1 and 3. This is a rare instance where you will get negative values for variables in geometry. It doesn't happen very often, but that's where you have to really do your homework and plug in the values. Overall, you don't want a negative length or a 0 length, but that didn't happen here, so we're good. That's where you, again, put in your values and check your work to make sure you can keep that solution. Because in geometry, there are no negative or 0 lengths. Okay. One last problem here and we're done. Whoops, I did not want to erase the fact that that was P. I'll put that back here in a second. Alright, what do we got here? This is point P. Alright, so, in this case, a little big one. So we got a two-parter here. So if CW, now CW has an equal, it's equal to 2z squared minus 5z minus 12. So that's a real quadratic equation there. And CP equals what? Z squared minus 15. Then Z equals what? And PW equals what? All right, so we have a two-parter. Well, CP equals Z squared minus 15. We can do that here, right? Here's where it gets fun. We know that CP would then be 2/3 of CW, right? Let's write that out here. CP equals 2/3 of CW, which would then give you that it's equal to, if we plug in these values here, that would give you then that Z squared minus 15 is equal to 2/3 of this honkin' thing here, 2/3 of 2Z squared minus 5Z minus 12. Well, if I were you, multiply both sides by 3, will you? So we can get rid of the fraction. Let's not deal with fractions. If you multiply both sides by 3, you'll get 3Z squared minus 45 equals 2 times 2Z squared minus 5Z minus 12. So now we no longer have a fraction, at least. Whew, for that, right? Let's do the distributive property. You'll end up getting 3Z squared minus 45 is actually equal to 4Z squared minus 10Z minus 24. Which now, let's actually make the left side equal to 0 and everything on the right. That's going to end up giving you Z squared minus 10Z, and then if you add 45 minus 24 is 21, plus 21. Okay, so now you end up having Z squared minus 10Z plus 21 equals 0. We just have a simple quadratic equation to solve, right? Which would end up then giving you simply Z minus 3 times Z minus 7 equal to 0. Of course, then take both of your solutions, set them equal to 0. You would have Z equal to 3 and then Z equals 7. Well, do your homework here. Just because you have a positive answer on both does not mean they're acceptable. Let me explain. If you stick in, let's do CP here. Stick the Z value in for that. Let's stick Z equals 3. So 3 squared is what? 9. 9 minus 15 is negative 6. Well, we can't have a negative length, so right away Z equals 3 goes out the window. Now what about Z equals 7? If you put 7 squared in, what do you have? 7 squared would be equal to 49 minus 15 would be 34. So yes, that is an acceptable answer. So Z equals 7. That's the only solution in this case, is Z is going to equal 7. Now, we got that CP is 2/3 of CW, but from the previous exercises, we also know that CP equals what? Twice PW. We ultimately need to solve for PW, so that means that PW equals half of CP. This is a big one, I'm sorry. Which would have to mean that PW equals half of what? Well, we just determined with Z equals 7 that CP is 34. So we have half of 34, which could only mean then that PW has a length of 17. So that was a really fun quadratic one. If you can remember that the medians of a triangle intersect at a point, or that point that they intersect at is always 2/3 of the distance from a vertice, and then just 1/3 of the distance from the midpoint of a side of a triangle, you got this. So that's it for this lesson. Next lesson we move into the right triangles unit, which I think a lot more people tend to enjoy that than what we've been doing lately. Maybe not the first lesson in it so much, but the subsequent lessons they will. The first lesson is about similarity in right triangles. We will get into geometric mean and those type of things. But then after that, we're on to Pythagorean theorem, converse of Pythagorean theorem, and then even some trigonometry. So I hope everyone has a great night. Take care.